Well, welcome to the question 2 from chapter 14, which is gas cleaning in fundamentals of particle technology. Again, I'm going to use the interactive question as a means of structuring the solution. The interactive question being here on the website. Let me explain what's going on in this particular situation. What we have is a settling chamber, which is basically a rectangular box with a flow rate into the settling chamber of Q meters cubed per second of gas containing dust particles. And the idea is that the flow comes in and the dust particles settle out in a similar sort of way to the Camp-Hazen model for a sedimentation settling basin. In other words, the critical particle trajectory is one that starts just here on every particular tray that we've got here, and the particle ends up captured on the surface of the lower tray just here before the gas flow leaves the device. So you'd have a straight line sort of illustration there of the critical particle trajectory, just like the Camp-Hazen model that we looked at in chapter 5, at the end of chapter 5. So the only way that makes any sense is that the flow through the chamber is fairly calm. There's no significant degree of turbulence in the gas flow. If there was turbulence in the gas flow, the particles would be forever being mixed up. So the only way that we can really apply a critical trajectory model here using the full chamber height is if the flow is relatively low, and clearly we're going to have to check the flow Reynolds number to check up on that. Okay, just to say a little bit more then. The dimensions of the chamber are given at the top here, and the width of the chamber is 1.5 meters. The height of the chamber, the total height of the chamber is 1.5 meters, and the question really is, what do we need to make the length of the chamber in order to remove the particles of interest, which are not yet defined as a size, but we are given some of the data for the gas flow. The gas viscosity 1.8 times 10 to the minus 5 pascal seconds. The density of the fluid is 1.2 kilograms per meter cubed. The density of the solids is 2,000 kilograms per meter cubed. We are given the particle size of interest. It's 50 microns. The intention is to remove all particles 50 microns in size. Okay, so we need the terminal settling velocity of the 50 micron particles, because they'll be settling downwards at the same time as being swept from left to right by the bulk flow. Okay, so it's very similar to the Camp-Hazen model, only we've split the flow up into 9 channels. You can see here 9 separate flow channels. We'll have to assume that there's equal flow over each one of these 9 channels. So we've got, what have we got, 8 plates there, 1, 2, 3, 4, 5, 6, 7, yeah, 8 plates, and of course there's the bottom of the device. So that gives us 9 channels in total. Okay, so the question starts off then by asking us to calculate the settling velocity using Stokes. So we need to remember some of these values just here because we'll be using them, but let's go straight over to pop Stokes' equation onto the whiteboard here. So we're after a settling velocity, so that's ut equals x squared, which we know is 50 microns, density of the solid minus density of the fluid, times by g, all divided by 18 mu. And if my memory is correct, that is 50 micron particle that we're interested in, but don't forget that's times 10 to the minus 6, and we need to square all that. Then we have a density difference of 2000, which is the solid's density, minus 1.2, which is the fluid density. Then of course we've got 9.81 all over 18 times 1.8 times 10 to the minus 5. There's probably too much there for my little calculator, so rather than use that, I've got here it pre-programmed into the spreadsheet. There's the diameter converted to SI units over there, the density of 2000 for the solids, the fluid density of 1.2, and that is in fact Pascal seconds, the viscosity of the fluid. And if you put those in and just check that I've calculated it correctly, yes, it's the diameter squared times by the density difference times by 9.81, all divided by 18 times by the viscosity on the bottom there. That all looks good. That gives us a velocity of 0.151 meters per second. It actually also gives us a particle Reynolds number of 0.5. It says there 0.504, which is actually higher than our desirable threshold. We like a threshold of 0.2 for streamline flow around a particle, for particle Reynolds number, and this is significantly higher. So we know the velocity will actually be less than 0.151, but don't worry about it, because the main aim of this question is to really work out whether it's a credible solution to have a laminar flow assumption of the fluid. So we'll stick with something which, if it doesn't work for what we're about to design, it won't work for something of an even slower settling velocity. That's probably the best way of looking at it. So we'll stick with 151 for the moment. So if we go back to here, and we're told to use Stokes's settling equation, so there's no problem with going ahead and doing so, and that's 0.151, and we find that's correct. That's good news. So we move on. Okay. We now want to calculate the residence time horizontally. Okay, so clearly we can calculate the residence time vertically from what we've just calculated, the settling velocity. Now we need to calculate the residence time horizontally. Now, the question here asks, select the best, i.e. easiest equation to use. And it gives us these four options. And this is where we have to take into account the number of channels, because the flow comes in and then we'll divide over 9 separate flow channels. So the flow down each channel is Q divided by N. But hold on a minute, the height of the channel is also going to be H divided by N. So in other words, the area that Q divided by N flow has to flow down is in fact the area divided by N, because area is equal to each of these heights times by W. So N cancels out. So although technically speaking the most appropriate equation to use probably would be C, there's no point using it. The easiest equation to use is A, because if we cancel out by the number of flow channels, calling that N, then it just gives us the same value as if we're calculating the ignoring the flow, all the flow channels. So let's check. Yep, that's correct. We don't have to worry about dividing by the flow channels for this part of the problem. We will have to worry about it for something else coming up, but that's in the future. Okay, so the residence time vertically, assuming the full height of the channel. In other words, each channel divider is of insignificant thickness, because we know the height is 1.5 meters, so we're just going to divide 1.5 meters by 9 to work out the height that we have to settle. So we know we have a velocity of, vertically we have a velocity of 0.151 metre per second, if we accept Stokes's the use of Stokes' equation there. Now the vertical height, we know the total height is 1.5 metres, and we need to break that up into the number of channels. So the vertical height is 1.5 divided by 9 gives us a height of each channel of 1.5 divided by 9 equals 0.167 meters. So each of those channels is 0.167, and we are settling at 0.151 meters per second. So ut equals height over time. So time equals height divided by ut equals 0.167 divided by 0.151. So the residence time vertically is 1.1 seconds. That's the time taken for the particle to deposit from going from the very top here to the very bottom there, for each of those plates. 1.1 seconds. There we go. It's that one there. Ready to answer. Quick check. Correct. Good. Ready to move on. Now we need to calculate the residence time. Well, we would be calculating the residence time horizontally if we knew what the length was, but we don't know what the length is. But we do know that we've got this equation here for the residence time horizontally, and we also know we've got a residence time of 1.1 seconds, which is the residence time vertically, and that's going to have to be the same as the residence time horizontally. So we can put this lot equal to 1.1 seconds. So let's have a go at that. So if we move up a little bit, in other words, we're not worrying about the number of plates because our equation for residence time, we decided didn't have to worry about that. So it's that is the volume, and we know that if we divide the volume by Q, it will give us the residence time in a horizontal way, which is going to be the same as the residence time in the vertical direction. So from that, we can work out that L, which is really what we're interested in here, is equal to Q times by T, Q times by T divided by H and W. It was 10 meters cubed per second, so that 10 times 1.1 makes that 11, and that is 1.5 squared. So 1.5 squared is 2.25. Better just check that rather than rely on memory. 1.5 times 1.5 is 2.25. So we've got 11 divided by 2.25. So my trusty calculator just here tells me that it's 4.9 meters. So the if we're going to go to the nearest meter, 5 meters is the length of the device that's needed. So we've got a 1.5 meter deep 1.5 metre high, 5 metre long settling chamber. Let's just check that that's the correct answer. Ready to answer? It's correct. Okay, job done. But is it? Because really, we need to calculate the Reynolds number to check that we don't have a high degree of turbulence, which would ruin our simple critical trajectory model. So we better do the check. Now, obviously we don't have a circular cross-section here, we have a rectangular cross-section. You have to think of yourself looking end on rather than sideways on, and looking end on the settling basin, you would have something in the order of a flow channel looking like this, quite squat. Okay, and we know that flow channel is 1.5 meters wide, and we know it's 1.5 meters high divided by the number of flow channels. Now we're going to want what's called the hydraulic diameter, which is always equal to 4 times the area open to flow divided by the wetted perimeter, only it's a gas, so we will just use the perimeter. Okay, so the area open to flow is going to be 1.5, so that's times by the width, 1.5, times by the height of the channel, which is 1.5, divided by n. The perimeter, that's n, not m. The perimeter is going to be 2 times 1.5 plus 1.5, again divided by n. Okay, so the area is just top dimension multiplied by the side dimension. The perimeter, though, is 2 of those and 2 of these, 2 of these, one there, one there, and 2 of these, 1 there and 1 there. Okay, we'll do a little bit of algebra here because obviously we want to try and simplify things. So first off, we can take that and make that into 2. That makes life simple. We can even take 1.5 out of everything. If we take that out, and that out, so that gives us now 3 over n on the top, 2 times 1.5 divided by n, and on the bottom we have just left 1 plus 1 over n. Okay, when we divide it through by 1.5, that would leave us with 1 just here, which is what I've got there. Okay, so that's 3 over n over 1 plus 1 over n. Let's tidy up the n's then. If we multiply top and bottom by n, then that becomes 3 over n plus 1. A much simpler equation to use. And we'll need that equation in a moment or two. Okay, well, we're after the hydraulic mean diameter. N in our case here is equal to 9. There are 9 flow channels. So if I just can slip this on, yes I can. So here we have 3 divided by 10. If n is equal to 9, then in other words our hydraulic mean diameter for this system is 0.3 meters. Okay, I think that was what the question was asking for. A bit convoluted, but worth going through carefully. The hydraulic mean diameter of the above settling system is 0.3 meters. Check. It is. That's good news. Right. Ready to move on. If we can do that. Now it's the big one. What is the flow Reynolds numbers? Okay. So let's go back. So we need the flow Reynolds number, which is du rho over mu. Only we'll use the hydraulic diameter. We'll need the velocity. We're going to have to calculate that. That's the velocity of the gas. And then we want the density of the gas divided by the viscosity. We haven't calculated the velocity of the gas yet. The velocity of the gas we're going to have to get from the continuity. The gas flow rate is equal to u, the velocity, times by the cross-sectional area. Again, we can use the full area of the vessel, because if we divide by the number of channels, n cancels out because the gas velocity, it makes no difference whether we divide by n or not. So that gives us 10 meters cubed per second is equal to ug, and if we're not if we're not dividing everything by the number of flow channels, then A is simply 1.5 squared. 1.5 squared. So ug is equal to 10 over 2.25, which is equal to 10 divided by 2.25, 4.44. So the velocity is 4.44 meters per second. I think we've got everything we need now for the Reynolds number. Just move it up a little bit. Okay, so we have our hydraulic mean diameter of 0.3. We have our velocity of 4.44. We have our density of the fluid as 1.2 kilograms per meter cubed, and we have our viscosity of 1.8 times 10 to the minus 5, and that obviously makes life quite difficult because that is such a small number. We're going to have a problem because the Reynolds number is going to be very high. That was our settling velocity. Let's move down a little bit. Okay. So what I've done here is, again, I've pre-populated. Yeah, that's actually the calculation for the number of plates. I've skipped the Reynolds number calculation. So I'll do that over here. It's a fairly straightforward calculation to do, so let's just plug the numbers in. We want 0.3 times by 4.44 times by 1.2 divided by 1.8 e to the minus 0.5. 88,000 is the Reynolds number. Let's just check that we've got that right. 88,000 is the Reynolds number. Ready to answer. Correct. What does that mean? It means the gas flow from left to right on each one of these channels is most highly turbulent. All these four answers were in the turbulent regime. It's actually 88,000, so we're miles off the arbitrary threshold between turbulent and laminar flow, which is around about 2,000 to 2,500. So no, it's a poor model. We can't use a settling chamber, a simple settling chamber like this, to remove 50 micron particles. But if we were to force the flow into being laminar, the sort of boundary layer flow type, then it would work. So what we'd have to do there is put in lots more channels, lots more plates. And if we put in enough plates, we could get to the point where the flow in the channel from left to right between each of the plates is laminar. So in other words, we can force the process to make it fit the model, which means that the design would work. So the question becomes, what's the number of trays that we need to add? Is it 36 trays, which is, this is the total number of trays rather than ones to add. Is it 36 trays, which is probably just about the limit of the sensible number of trays to put in? 175 is crazy. In 1.5 meters, that's not crazy, and the other two are even crazier. So let's see whether we can force it into some sensible solution. Now, to do that, we're going to need to decide on our Reynolds number threshold. And if we say that the Reynolds number threshold is, let's say, totally arbitrary 2,300. Okay, we know our equation for hydraulic diameter is this. It's got n in it, which is what we want because we're changing the number of trays. So we have an equation here which is 3 over n plus 1 times by, this will always be 4.44 regardless of the number of trays that we're using. This will always be 1.2, again regardless of the number of trays using, and the viscosity is also a constant. So that is the equation, and that's the equation that we're rearranging to work out the number of trays to force this into laminar flow, or to force it into a flow where we've got 2,300. So the first thing to do is obviously to take that over here and take these two and divide over here, and that's what I've done on the spreadsheet already. So if I can get back to the spreadsheet, let's move it over here, that's okay. So we've taken an arbitrary threshold of 2,300. The 2,300 times by the viscosity divided by the velocity and the density gives us that value. Now that is 3 over n plus 1, so n plus 1 is equal to 3 divided by that value, and that gives us 386. So if you take away the 1 from both sides, that actually leaves us with 385 trays as the answer. So the number of trays required to force this into laminar flow is 385, and putting 385 trays, or 384 trays actually, because we're using the base as an extra tray, so 384 trays in that 1.5 meter height isn't going to work. So what that's telling us is that sure, you can design the process and have a 5 meter long rectangular settling chamber for removal of particles 50 microns in size, but it's not going to work because the model we've used is too simple. We've assumed a laminar model for the flow of the gas through the chamber, whereas reality is that we've got a Reynolds number of something like 88,000 with the 8 trays in 9 channels, and that is highly turbulent. The particles, the 50 micron particles, will not be allowed to settle. They'll be forever being redistributed by the flow of the gas, the turbulent flow of the gas. All is not lost. It sounds depressing, but all is not lost. All we need to do is design this for turbulent flow. You know, we can do that. The critical particle trajectory model clearly doesn't work using the full channel height available between the two trays, but the critical particle trajectory model will still work in a differential amount, in a differential distance, only we then have to integrate over the whole of the distance to find out how many particles we've captured. So we can actually still use the critical trajectory model, but not over the whole device, only over small elements where we're in what is flow from left to right, which is going to be a differential equation rather than a macroscopic algebraic equation. So what is not lost is just that we have to adapt the model to fit the situation being driven by the fact that we've got 10 meters cubed per second flow rate, which is obviously quite a high flow rate, but fairly typical of gas effluents in industrial processes. So the next question is how to deal with the fact that we have the turbulent flow. It's the same system, but we will take into account the turbulent flow. Okay, that's it then. Bye.